Good morning again. I'm actually an emergency nurse and a volunteer firefighter. So when I explain now why this is important for Campus Vesta, I'm going to tell you a personal story. As an emergency nurse, I always go to immediate crises. So I treat people when in distress at the moment. And as a fireman, I did the same. A bit different, I was fighting fires. But then I became president of the Campus Vesta. And now I am confronted with the historical PFAS in the ground. And those two types of emergencies and addressing emergencies are in conflict with me. Because I still think it's necessary for the firemen to maintain a capability to put down fires, and especially fires that are quite dangerous for the environment or for the fireman itself, look like the petrochemical industry in the port of Antwerp. But also, as an emergency nurse, I think if it's possible to do it with foam that is capable of pushing out a fire, but don't need to exaggerate any additives in the foam that are bad for the environment or for the health of the community. So if I address why is this important for Campus Vesta, I think it's clear. We do have a historical pollution on our fields, also in the ground, but in the ground level waters also. It is because we are specialized in training for industrial fires. We have a large site that treats and learns firemen to address those fires. And the historical pollution dates from before 2011. Why 2011? Well, we have here a water treatment, a biological water treatment. And that's why we needed to get rid of the foam with every stuff in it, because our biological water treatment needs to be at its utmost performance. So we use training foam. It's not the same. Firemen still are telling me that the foam disappears quite fast, but for training solutions, it's perfect. And I also know that the professional fire stations are switching their foams to PFAS-free foams. But also we need to address that the large industrial and chemical plants still need those foams with the capability of put down the fire if necessary. So again, why is this important, and why does Campus Vesta put his terrain at the good hands of the laboratories, but also at C-biotech to clean out the soil? I think it's clear. And that's why we at Campus Vesta are still, and we're reaching out to maintain this level of solutions, of trying to see solutions for the future. So I make it very short. The terrain is still open, Frederick, for maintaining this project, spanning out the project. We still have ground enough who is polluted and can be of use in the near future. But I still want to maintain the solution has to be in balance with the things firemen need to put down the fire. And it's sometimes a difficult question to maintain here at the school. And I'm very glad to see that there is some light at the end of the tunnel, that we might have a solution to put down in large scale, because this was, I think, a small scale exercise, but maybe we can put it in a large scale. So I thank you again. And I will ask C-biotech Erik to maintain and explain us what we did here and what the results were.
Thank you. Yes, good morning. Thank you, everyone, for your presence and your interest in the results of our investigation, our phytoremediation experiment here at Campus Vesta. We didn't do it alone. It's clear we had several partners, not only partners, but as Luc said, also an analytical watchdog, which was very important. Watchdog, like he said, that gave us state-of-the-art analysis. We also work together, of course, with Campus Vesta and the province of Antwerp itself. I want to thank the leadership of the campus and also the province for their vision on the future and to give us a chance to develop new techniques which are probably much less invasive than the techniques we use today to clean up PFAS in the environment. Another partner was DEME, and is DEME, who gave us the necessary logistical support. And the key partner in this all was the Dutch company of Bertels. They have already almost 30 years experience with the development of bio-based additives to help hemp plants grow. Hemp plants have a lot of things they can deliver to society. They have it's in fact the fibers of the plant are used in different types of textile, building materials, and so on. But it was rather new also for Bertels to use the hemp plant also for phytoremediation. It was already known in general that hemp has the capacity to clean up the soil, not only from PFAS, but also from other contaminants. But up until now, it was a very slow process. So in the former experiments that were done worldwide, but also here at, with C-biotech in 2022, in the vicinity of the 3M plant at Zwijndrecht, it was already shown that the hemp plant has this capacity, but it went very slow. So you needed more than 10 years to clean up a moderately contaminated site, which is, of course, a long time. So together with Bertels, we tried to find solutions to that problem. Campus Vesta is, as Pieter already explained, is a very interesting site to do this experiment. Why? Because the contamination is caused by the use of fluorinated AFFF foams, so the anti-firefighting foams that contain fluorinated compounds. And in fact, in that sense, it's very representative for a lot of contaminated sites. If we see, for example, in Flanders, there are already a few hundred contaminated sites registered by the OVAM that are more or less comparable to the situation here. So there's a broad terrain where we can work with this technique in the future. First step, of course, was to set up an experimental design. We had around 3,400 square meters of terrain that was available. We divided into 25 subplots. That's to say we had 9 bigger subplots which were free to interact with the groundwater. But we also isolated a small part of the terrain and we divided it into 16 squares. Why? Because we also wanted to have a backup for everything we were doing in the open fields, but also because these 16 squares are not in interaction with the groundwater. And that's very important because we wanted to know if there is some interaction with groundwater, for example, if the groundwater mounts, and that can be expected if you have, for example, like last year, a very wet spring. if the groundwater mounts, does it bring new PFAS, or if it rains a lot, does it leach out the PFAS into the groundwater? We wanted to exclude that. We wanted to see that we had a clear picture of all the dynamics of the PFAS transport. Then in those 9 subplots, we used several additives, mainly provided by the Bertels company. There was also another additive, but mainly provided by the Bertels company, and also their combinations. To be very clear, all those additives, they are man-made, but they are bio-based. So we are not introducing anthropogenic molecules into nature. Everything we use can be biodegraded after a while. So it was a very complex structure, and the result was that we had not only in the end at the harvest season in September, in the middle of September, we didn't not only harvest around 3 tons of hemp, but also and more importantly, we had a really huge stack of analytical data, and we took the necessary time to study all those data and to make some conclusions. Those conclusions we can make different conclusions, but maybe the most spectacular one was that an additive that we developed together with Bertels on the basis of additives that are also used to transport the nutrients in the soil towards the plant. We found out that it also can be used to transport the contaminants towards the plant, and that led to some quite spectacular results, in fact, in one of the subplots, where we used this hempurizer, where we could see that especially the PFAS, which is a longer chain, which is also a very stubborn chain that stays in, it's very difficult to remove it from the soil, but that we succeeded in removing it and to mobilize it towards the plant. And that's very important because PFAS is, together with PFOA, it are the two most common and most known PFASs, but they are also very toxic and they are widespread in the environment. So to explain more into detail the results of the experiments we did, I will give now the word to Professor Ingmar Nopens.
Okay, thank you very much. And also from my end, good morning to everyone. So as Luc and Erik already explained, after this experimental setup, we end up with, and I think I was also thinking about the iceberg analogy. You have tons of data, okay, it's not that data is in front of you and that you immediately see what the conclusions are. So you have to dive deep, dig deep, brainstorm, and check what can be made out of it. So I will walk you through some of the results, but I would say it's still the tip of the iceberg. That's why the report is also called 1.0. So we'll dig further into it. But nevertheless, the results that we have already obtained are very groundbreaking, I would say. So what you see on this plot is just walk you through. So on the horizontal axis, you see the different subplots. So the large subplots that Erik talked about, the 9 subplots where we used different additives. And then on the vertical axis, you see the concentrations of PFAS. So we're talking here about PFAS, which is the sum of all the the target analysis, the different compounds, the 36 compounds that were measured. The color codes that you see, the sum of the green and the red, that's the initial value. So that's the initial value that we measured back in June when we started the experiment. And then the green one is the one we ended up in the end of the experiment, so the end of September, and this is PFAS in the soil. So what you can immediately observe is that in all the subplots that we studied, that we see a vast decrease in the PFAS concentrations. Okay, so that for us was important because again it confirmed that the hemp plants can remove PFAS from the soil. Okay, that's a first observation. Other observations that you can see is that the different plots, there's quite a variety of concentration. Yeah, and I'll show that in a bit also in a spatial context. That was also a bit surprising. But another thing that is important, if you look at the yellow line that is indicated here, the yellow line, that is actually the legal norm in Flanders for PFAS, which is 3.8 microgram per kilogram of dry matter. And actually what you see is that most of the parts, even the ones that were initially above that threshold, are now, after one cultivation, below that threshold. And that is a very important finding. It was already indicated by Erik that this is really the speed that you need also for a technology to be viable. Okay, so that is first result. If we then look at the spatial distribution of the PFAS, sorry, it's a bit slow, so I press twice. I'll go back. So here, what you see is the Vesta plot. On the left-hand side, it's again the initial condition, the initial situation in June. And at the right-hand side, you see the situation in September. The first thing that we see on the left-hand side, and so basically the way we plotted this is we had measurements in all of the 9 subplots, and apart from that, we use an interpolation algorithm to make this heat map. At the beginning, there was before we started the project, there was already a soil research done, and this was done on 2 locations. It was somewhere here in the middle and somewhere down here. Okay, and so if you look at the color codes that we see here, we found like values of 14, 15, and it seemed to be quite homogeneous. Yeah, so it was when we saw these results, was a bit surprising that this was the case, and this is really important because when you look at any contaminated site, yeah, you don't see where it is. Apparently, you have hotspots or spots with higher concentrations. You have regions with lower concentrations. Okay, and that's very important when you design a technique to remediate it. It would be really good to get insight into that. I will come back to that later. However, if you then look at the right-hand side, you see again that now, so if you look at the color codes, I didn't mention that, the blue one is low concentrations, red one is the highest concentration. Okay, so the good news is that after one cultivation, we see that actually the northern part of the site is now already completely below the legal limit, and so we are only ending up with 1/3 that needs probably a second treatment, and after that would be in also below the limit.
Excuse me.
Yep.
What is the highest initial concentration? Because it's not readable.
The highest initial concentration is 29. Yeah, so around 29. That was the highest one that we had here. Okay, so now we see that PFAS is being removed from the soil. The next question is, okay, where did it go? Okay, so as Luc explained, we also took samples of the leaves at different time instances and looked at the concentrations in the leaves. And why the leaves? Because the way a plant works, a plant takes up liquids from the soil because it needs nutrients. And of course, all the molecules that are present there will also be taken up. Liquid goes into the leaves, and there it is being evaporated. And the larger molecules that cannot evaporate, and for sure these can't, they will just remain there and sit there. That's the reason why you have these concentrations in the leaves and not in the stem of the plant. Top left figure, what does it show? It shows us in green, so this is a logarithmic scale. So in green, it shows us the concentration in the leaves, whereas the blue one shows us the concentration in the soil. And on the horizontal axis, we have, again, time. So it's 1 monthly measurement. So what you observe is that, and this is for one plot, what you observe is that after 1 month, even initially, you already see that there's quite some taken up. But again, it's a logarithmic scale, so be careful to read it. But we end up after 1 month already at the plateau. So you already have a kind of a saturated value. That doesn't mean that the remediation stops there, because the plant is growing and is making more leaves, meaning that, okay, in that way you're taking up more contaminants. And then if you look at the soil analysis, you see that it goes down, goes up a little bit here. Again, that's because of the logarithmic scale. We also have an explanation on that, but I will not go into that amount of detail. So that's one good thing, is it's removed from the soil and we find it back in the leaves. Then, of course, this is a sum of PFAS. So then we have to go one level deeper and look at, okay, which type of PFAS are we looking at? And one plot that you can see down here is then not distinguishing based on every single molecule, but distinguishing on the chain length. Okay, and as explained already before by Luc, the longer the chain length becomes, the more hydrophobic the molecule becomes, and the more difficult, the less mobile it is, and the more difficult it is for the plant to take it up. And that's actually what you also see here. So if you look at the green, you see that the shorter chains are taken up more than the longer chains. Although we still have longer chains in the leaves, which means that they have been taken up, and that they were able to be taken up. By the way, this is in percentage, so this is the percentual what we see there. What else can we appreciate? Or another typical value that is calculated in the literature is the BAF, or the bioaccumulation factor. So that is basically how much, what is the amplification of the concentration that you measure in the leaves compared to the concentration that you measure in the soil. And so here we found in the best performing plot, plot 9, we found that it was 27. Yeah, just to give you an idea, if this is above 10, a plant is considered a hyperaccumulator and is something that is good for removing, for phytoremediation. So for the other plots, we found 7.8, and why is that different? Well, that is basically different because of the additives that we have added. Okay, so. But this is also in line with what we find in the literature. Okay, so that is fine. That is good. Okay, that's the PFAS story. Let's then go to PFOS. The PFOS is one molecule with a chain length of 8, and as was already explained, these are the more tricky ones, but also the toxic ones. So it's important that we focus on those and make sure that these are also removed. Plot that you see here, similar as the previous one, and you can actually appreciate that most of the PFAS that we encountered is actually PFOS. Okay, so that is what we see here. But again, the same observation. We start with high values, and we see that we have vast reductions in PFOS concentrations in the soil. And again, for most of the subplots, we are below the Flemish legal limit, which is for us important. And again, with one cultivation, yeah, which is important because in the international literature, it's often said, okay, this is an interesting technique, but it takes ages to complete. Yeah, and what we find here is that that is actually not the case for what we tested. And then, of course, you see also that there's a variability between the different plots. Okay, if we then also calculate the BAF, the bioaccumulation factor for PFAS, you see that it is typically lower. Yeah, so in some of the plots, we find 0.14 in the literature. We find a similar value that is reported. However, in our highest performing plot, we see that we obtain a BAF of 0.83, which is almost 8 times larger, which means that the PFAS is taken up 8 times faster than compared to the plot, the neighboring plot. And that is a very important finding, and that was in the plot where we used the Hempurizer Plus. Okay, we can go another level deeper, and I will not go too deep. Don't be worried about that. But here we now we focus a bit because we see that this plot 9 is really something where we see very interesting results. So we dug a little bit deeper into that one. And so on the left-hand side, what you see are on the top one is concentrations in the initially in the soil, at the end in the soil, initially in the plant, and at the end in the plant. Yeah? Okay, and these are concentrations. The bottom one is the same, but percentual, because otherwise you cannot see what the composition is. So that is just a percentual composition of what you see there. In this plot over here, it's just the soil, beginning, end. And here we have listed that up in terms of chain lengths. Okay, so you can already start appreciating that it's not a walk in the park. You say, oh, this is what is happening here. So we need to start making hypotheses of what is going on there and what we actually observe. Okay, so if we look here to this graph, you can see that you have, and that's also what you see here, you have a part with longer chains, you have a part with shorter chains, and then you have in the middle here the PFAS, right? And that's also what you see here. And by the end of the experiment, what you see is that most of the long chains are no longer present, and most of the short chains are also gone or removed. If we then look at the plants, here you can of course see it. So the up concentration, the BAF. So you see much larger concentrations over there, and there the gray part is mainly the shorter chain PFAS that you observe. Right? And why is that? That's logical because they are more hydrophilic and they are taken up much faster. Okay, but what we observed here in this particular case, or the case where we used the Hempurizer Plus, we observed actually molecules in the leaves that were actually originally not present in the soil. Yeah? Okay, so that was an interesting finding. Because what is happening there, they cannot just, the law of physics, they cannot just appear or disappear. They have to come from somewhere. And Luc already explained the story about precursors. So they have to come from somewhere. And so our hypothesis is that these molecules that we find there, that they are actually converted from either the longer chains and partly also from the PFAS. And if then you start calculating, okay, it's a small concentration, but if you then start calculating for these, and I was talking about these three, I will I will spare you the names. But if you calculate these three, and if you add them to the removal of the PFAS, because they are actually not directly removed, but they are first converted and then removed. I'll show that on the next slide. Then you find a buff of 2 to 3, depending how much you take them into account, which means that you have a factor of 20 to 30 faster removal of this PFAS. And that is actually the reason or the explanation why we saw this, fast removal of the PFAS, let's say a step ahead, a huge step ahead compared to the previous studies that we did, and also what is reported in the scientific literature. So this is a bit what I was saying. So on the left-hand side you have the soil, and on the right-hand side you have the leaf. So in the soil, initially you have long-chain PFAS, you have PFOS, and you have the short-chain PFAS. The short chains, they are taken up immediately. Then you have the long chains. They are more difficult. They will hardly be taken up. We don't find them there. So likely with the hempurizer, they will be converted into PFOS. And then the PFOS is likely converted into these other molecules that were initially not present, but that we find back in the plant. Okay, so in this way, it's a bunch of data, and you have to unravel it and try to figure out what is happening there. But for us, this was a very enlightening thing. And the point is, so this was one large subplot. We applied it also in one of these smaller subplots that Erik was talking about, and we saw exactly the same trend in the subplots where we applied this hempurizer. Okay, so that kind of confirms that, and we didn't see that in the other plots. So that really confirms what is going on. Yes?
And can you explain this, why the hempurizer is this capability of doing something?
Yeah, so as Erik already explained, the hempurizer is a product that is basically developed to facilitate the uptake of nutrients by the plant. Okay, so we don't know the exact thing that is happening, but it will make the molecules more available to be taken up. And if you look at this here, it means that it actually also, so PFOS is basically, it's a long molecule, and basically it likely breaks one carbon-carbon link, breaking it up in smaller chains. And the smaller chains, again, become more hydrophilic and can be taken up easier through the... No, indeed. They targeted different, so one was more to stimulate the roots, the other one was, so they had different objectives. And so this one really, okay. So that kind of almost brings me to the end, but I also wanted to add a little overview of what that, again, in terms of viability of the technology. We made a simple comparison between the cost to treat a certain piece of soil. So I based it here on the case of Vesta, so 0.3 hectares and a starting concentration of 30 micrograms per kilograms of dry matter. And if you make the math, you will see that actually we can, with this technology, we can do it in a quarter or a third of the cost. And another thing that was already mentioned, Luc emphasized also sustainability. If you do it the traditional way, you'll have a vast CO2 exhaust, whereas here we could even go CO2 negative. Okay, I haven't talked about destruction. That's another thing we have to accommodate. But for now, the plants take up CO2, so they will contribute to, will do it in a more sustainable way. Brings me to the conclusions. So a couple of things that we learned. The heterogeneity, I point your attention to that as well. It's not because you have a plot and you do 2 measurements that it's homogeneous and everywhere. That's important because it will also tell you what type of treatment you will have to do. It's like a surgeon. If you go to the doctor and he says, "Yeah, we have to operate completely," and otherwise you can really, in a targeted way, work with that. Okay, we demonstrated that both PFAS in general and PFOS were vastly decreased. In one cultivation, we could get 2/3 of the plot below the legal limit. We found increased concentrations in the leaves, so it proves that the plant actually takes up the PFAS. And with that, with Hemperizer Plus, we see that we have high buff values, both for the total of PFAS, but especially also for the PFOS, which is already 8 times higher. And then the fact that we saw also conversion and other shorter chain molecules pop up in the plants, meaning that if you add that, you even end up with a factor 20 to 30 more. And then the last part is also important because at the beginning, and maybe that's a little anecdote. So we also are involved in a KISS project, so the Knowledge Institute for Sanitation, for Innovative Sanitation Techniques for PFAS. We wanted to use the site here as a case to further continue this work. And at the beginning, I was like, "Oh yeah, you should not take a site that has too high contamination." And now actually, after 1 year, we are so low that they say, "Yeah, you better find another location with a higher concentration because otherwise maybe the findings will not be that." But what is important is that indeed by speeding up the removal by 20 to 30 times, you actually open up the land area that you can treat with this. Initially, we had also the figure of 30 in mind, like, okay, that's the maximum, and then it will take a couple of years. Now we are convinced that we can actually also treat higher contaminated sites, which means that, so mildly, it's still mild because we don't want to go to 2,000-3,000. That's not our aim, but everything within 100 micrograms, I think, is within reach, and a lot of the contaminations are in that area. So 85% is an estimate. So to end with some perspectives, as Pieter already mentioned, we will continue the work here at Vesta. So we will clean up the rest of this site. So then we have I think the first one that is completely treated with phytoremediation. That would be a nice one globally. We will further test with Bertels and further improve, because 20 to 30, maybe we can even further improve it. That would be even better. We will also test other types of polluted sites where, for example, PFOA is more abundant. So we have already some sites that we will target both in Europe and in the US. The destruction is the other part. I haven't addressed that. That's part of the KISS project I was talking about. But we have some other ideas to work on that, because that's another very important. You can up concentrate and put it somewhere, but you don't want to end up with the next nuclear waste problem. So you also need a solution for that. And then we also want to develop a method to work on this heterogeneity that I was talking about, so that you're not blindly working on a field. And we're working on kind of a scanning technology, based on hyperspectral data and artificial intelligence. But that's something that is currently being developed. But then you can really, in a more precise way, say, okay, maybe this part we need to excavate, that part we will put this, that part we will put that, and maybe also know how much of the Hemperizer Plus we need to add. Okay, so I'll keep it at that. And I would like to again thank Campus Vesta for doing this project, and all our partners and our watchdogs to help us out with this project and to make sure that we have sound results. Yeah.
I have two questions. The first one is, what happens with the plants? Do they get burned, or how do they get?
No. So at this moment, we just harvested them and we actually now palletize them, and they are now waiting. And so one technique that we will investigate is pyrolysis to see what that can do. And we have another one in mind. But to give you an idea from this one, there's not too much. It's a couple of tons of material. So we have it safely stored for the moment.
That treatment is not calculated in the price of the cost price that you mentioned earlier.
Yeah, yes, it is. It is.
Oh, okay.
Yes. Yeah.
Second question, you treated an area specifically with the plants. What happens with the area next to your plants? Is it also better, or did you take some heb je daar ook staling doen?
You mean the surrounding?
Yeah.
No, we did not do that, but I would not expect. I mean, since it's kind of a pumping, I would not expect it to take away pollution that is further away from that. So I would not expect that. We could check it, but I think that would be a long shot. Yeah.
Can you take a sample at a certain time on a certain plot? How many samples were taken?
Maybe Erik, you can.
We took one sample in each subplot and also in the 19 smaller plots, or the 16 smaller plots, once a month. We took one sample at a fixed point, and we also took a mixed sample of randomly chosen places in the subplot. We mixed it up together. It was a mixed sample, and then we to be sure that the fixed place where we took the sample every month, that it was representative for the whole of the subplot.
These results, they tell us something about the top 50 centimeters of the terrain, I think. What about deeper contamination? Because classically, Pieter's contamination goes to 3 meters below surface. Because you say that you're going to treat the terrain completely, but can you really say that?
Yeah.
It's only telling us something about the top 50 centimeters.
Yeah. Well, this has to do with the depth of the roots. So I think the hemp plants, they go quite deep. I would say 1 meter. The point is, if you really want to go deeper, then you have to, for example, go to willows because they really go a lot deeper.
And here on this side, it's a surface contamination then.
Yes.
Yes.
Yeah, definitely. We took samples at 20 centimeter and at 50 centimeter. And at 50 centimeter, there was almost no PFAS present in the beginning. Okay. And it stayed unchanged during the process. Yeah. So there was also no leaching out.
Okay. That was my second question.
Did you also have a collection of other pollutions, like heavy metals?
Right, we did not investigate that here. No.
I can imagine this process needs a lot of water. And did you already think of a method you can use in Spain or in Italy, where there's not enough water to grow hemp or willow?
Yeah. Well, here we had a lot of water. For sure. That was not a problem. No, the point is that hemp is actually not a very thirsty. So if you compare it to other, let's say, traditional cultivations, it can use less than 90% of that. It needs water to germinate. And I look also at the experts there. It needs water to germinate, and of course it needs some water. But indeed, it's something to be cautious of, that you can irrigate. Because if it's dry, you will have to foresee something. Yeah. Yes. I mean, otherwise a plant cannot survive. It's nature.
Thank you.
Ja.
Is er in eerdere proeven bewezen dat een tweede teelt inderdaad cumulatief is? Of zou het kunnen zijn dat er een deel is dat je er niet uitkrijgt?
Eigenlijk twee teelten na elkaar. Ik denk niet dat dat al, zelfs niet in de literatuur, gebeurd is. Het staat gepland in ons KISS-project, willen we dat eigenlijk op potproefniveau gaan doen. Om net die vraag te beantwoorden. Maar het zou mij sterk verwonderen, want anders zou je nu een bepaalde molecule daar terugvinden die niet verwijderd wordt, dan zou die daar denk ik uit schieten. Dat is mijn aanvoelen. Maar ik denk niet dat op dit moment, dus dat is iets dat nog op onze onderzoeksagenda staat. Okay. If there are no more further questions, then allow me to thank you all once again for your presence. And
Please contact us.
And please contact us. Yeah, you have all the. Send us an email. Have a look at the website, and you can actually download the report also shortly from the website.